Welcome to the Solutions Part 1 Screencast for Chem 1B at Shasta College. So far in the Solutions unit, we've mostly dealt with what's probably the most common type of solution, which is solid dissolved in a liquid. But of course there's plenty of other types of solution, and the one we're going to look at next is a gas dissolved in a liquid. A couple important examples of this. Oxygen is able to be transported throughout the body, and carbon dioxide is removed from it, partially because both oxygen and carbon dioxide are somewhat soluble in blood. And there are a number of beverages that are enhanced when carbon dioxide is dissolved in them, making them fizzy or carbonated, and beer is a great tasting example of this. Now, when we look at the solubility of a gas in a liquid, the solubility depends upon what specific gas we're dealing with, what liquid it's dissolved in, the temperature of the solution, and the pressure of the gas above the solution. And for a particular gas in a particular liquid, if we measure the solubility of the gas at a particular partial pressure of the gas above the liquid, and then increase the pressure, we find that the solubility increases as well. And when we decrease the pressure, the solubility decreases, and the graphical relationship is shown here. It's a linear relationship, and this is true in general for gases. Now, a particular gas will have a linear relationship between solubility and pressure, but the slope of the line will vary from gas to gas. Now, of course, what this means is gas solubility is directly proportional to the partial pressure of the gas, and the mathematical relationship is shown here, where solubility is represented by C for concentration, and this is of a specific gas, so we sometimes put a subscript G to indicate gas, or we may use a subscript of the specific gas itself. Now, this is directly proportional to the pressure P. Please note it's a partial pressure. It's the pressure of just that particular gas. So again, subscript G is sometimes used, or the specific gas is used as a subscript instead. And then the proportionality constant is a little k, which is a Henry's law constant. And there's sometimes a subscript H there to indicate Henry's law. And for a particular gas, there is a particular Henry's law constant. And in fact, the Henry's law constant also depends upon the solvent, and it's going to depend upon the temperature. So this is what's known as Henry's law. Now, the Henry's law relationship can be solved for the Henry's law constant, and the concentration over pressure ratio is therefore equal to a constant. And so if we have one set of circumstances compared to another set of circumstances for a given gas, then the concentration to pressure ratio remains constant. In other words, C1 over P1 equals C2 over P2. And this is another form or version of Henry's law, and this can also be useful in solving problems. So let's solve a problem. Example 5 deals with one of our favorite beverages, Chem Cola. Like other colas, it's bottled with a pressure of carbon dioxide, in this case 3.6 atmospheres above the liquid. And the question is, what's the concentration of CO2 in Chem Cola? And to solve this, we are also given the Henry's law constant for CO2 at 25 degrees Celsius. So to solve this problem, we need to note that the concentration of the particular gas, in this case carbon dioxide, is directly proportional to the pressure of the gas, and the Henry's law constant is for that specific gas, and the pressure is for that specific gas. The Henry's law constant for CO2 is 3.4 times 10 to the minus fourth, and the units are moles per liter atmosphere, and the pressure above the liquid is 3.6 atms, and atmospheres will cancel, and when we multiply the two numbers together, we get 1.2 times 10 to the minus third units of moles per liter. And if you want to be specific, it's moles of CO2 per liter of solution, which in this case is, of course, Chem Cola. And so there's one form, one way to write the answer. And I'll just note we could also write it in non-scientific notation, and we could also use the molarity symbol, capital M, instead. So this would be an alternative form of the answer. Now, if we look at the relationship between gas solubility and temperature, it turns out that as we increase the temperature of a solution, gas becomes less soluble in it. And if we decrease the temperature of the solution, gas becomes more soluble in it. This is shown here for carbon dioxide and several other gases. And what this means, of course, is in general, for gases, temperature and solubility are inversely proportional to each other. And you've certainly experienced this before. If you've ever had a carbonated beverage, when the temperature is low, there's a higher concentration of CO2 and it's fizzier. And when the beverage gets warm, there's less CO2 and it's not able to be as fizzy. Now, your friendly neighborhood instructor grew up in the frozen tundra of Wisconsin, and there it gets really cold, which makes the roads icy, and to keep them from being icy, it's pretty common to dump salt on them. Now, this is an example of adding a non-volatile solute to a solvent, which ends up lowering the freezing point of the solution that's made. Note that non-volatile solute means that the solute doesn't evaporate very easily, and salt is, of course, an example of that. And the solvent in this case is water, and so the salt and water mixture freezes at a lower point than 0 degrees Celsius, which means that the roads aren't going to be icy at 0 degrees. They won't freeze until somewhat lower than that. And how much lower depends upon how concentrated the salt and water solution is. And the relationship is shown in this equation, in which the delta T represents the temperature difference between the freezing point of the pure solvent and the freezing point of the solution. And there's an F here to indicate it's a freezing point temperature difference. It's directly proportional to the molality of the solution, and this is moles of solute per kilogram of solvent. The proportionality factor is called K sub F for freezing point constant, and there is also another factor called the Van't Hoff factor, and this is something that is needed to take into account the fact that in some solutions, when they dissolve, the amount of solute, when it dissolves, actually makes more pieces, more total particles. And so, for example, if we have a molecular compound, 1 mole of that compound makes 1 mole of particles when it dissolves. But if we have an ionic compound, such as sodium chloride, when it dissolves, it makes an Na plus and a Cl minus, so it makes 2 particles, 2 ions for each unit, each NaCl unit. And so the Van't Hoff factor here would be 2 because of the dissociation of NaCl into 2 particles. So here is an example of that. Example 6, road de-icing is done using different salts, typically sodium chloride or calcium chloride. And so in this particular case, we have 38.7 grams of calcium chloride added to 235 milliliters of water. And the question is, how low a temperature is needed to make the solution freeze? So in this case, if we're dealing with freezing point being lowered, the relationship is the one we just saw. The temperature difference between the freezing point of the pure solvent and the freezing point of the solution depends upon the freezing point constant, which is a specific value for a specific solvent. It depends upon the molality, and it depends upon the Van 't Hoff factor. Now, in this case, the freezing point constant for water is 1.86, and the units are degrees Celsius kilogram per mole. And freezing point constant values are things that are found in tables. You can look them up, and they've typically been determined by experiment. The molality, in this case, is going to be moles of solute, which is calcium chloride, divided by kilograms of solvent, which in this case is water. And the Van 't Hoff factor is for calcium chloride, and calcium chloride dissociates in water into a calcium ion +2 charge, and a chloride ion -1 charge, and another chloride ion -1 charge. And that means we have a total of 3 pieces, so the Van 't Hoff factor is approximately 3. It turns out that the Van 't Hoff factor depends also on concentration. More on that in a bit. So, to solve this for calcium chloride, what we know is we have 38.7 grams. The molar mass of calcium chloride is 110.98, so that number of grams per 1 mole. And that turns out to be 0.349 moles of calcium chloride. For kilograms of water, well, what we have for water is 235 milliliters, and 235 milliliters is about the same as 235 grams, and 235 grams is about the same as 0.235 kilograms. And so we now have the number of moles of calcium chloride, we have the number of kilograms of water, we have the freezing point constant, and we have the Van 't Hoff factor. So that's all we need, and we can plug this into our freezing point constant equation. 1.86 degrees Celsius kilogram per mole. Moles of calcium chloride is 0.349. Kilograms of water is 0.235. And Van 't Hoff factor is 3. And what we end up is kilograms and kilograms cancel, moles and moles cancel, and 1.86 times 0.349 times 3 divided by 0.235 gives us about 8.26 degrees Celsius. And what this means is the solution will freeze about 8.26 degrees lower than that of pure water. And since pure water freezes at about 0 degrees Celsius, then how low a temperature is needed, so the actual temperature that is needed to make the solution freeze, is going to be a little less than, or a little lower than -8 degrees Celsius. And let's call it about -8.3, because typically the Van 't Hoff factor is not known, or it's not, it's probably more than 1 sig fig, but it's probably not more than 2. So there's an approximate value for the temperature needed to freeze this solution. And that's it for screencast number 1 for solutions. Check screencast number 2 to follow.